Hello and welcome. In this video, we're going to take a look at a nice little shortcut if you have to add up a bunch of terms with a repeating pattern. Something that would be simply like an incremental change from one term to the next. And so we call this sigma notation, or if you want to, you could call it summation notation. And it uses the capital letter sigma, which corresponds to the capital letter S. S for sum, kind of makes sense, but it has these little components below and above, a subscript I equals some number m, and a superscript, which is just a number such as n. So let's take a look at what these different components mean. So first of all, the symbol, capital sigma here, this is telling us that we need to add. If you want to multiply a bunch of factors with some sort of pattern from one factor to the next, then we would use a similar notation with a capital Greek letter pi. But we're using summations, so we use capital sigma. At the bottom here, we have I equal m. And this tells us, if you think about I as being an index, it's going to be starting with I equals m. Now, at the number at the top there, well, we take I to be the index all the way through our summation, and the index will increment 1 at a time. So starting at m, going to m plus 1, going to m plus 2, and we'll just keep that pattern going until we reach this particular number n, which is where we've chosen to stop this sum. We don't write I equals n, but we just assume that, of course, we're talking about I this whole time, and I will stop when we reach the number n. And so we increment I from one number to the next when we go from one term of the sum to the next term of the sum. In this case, we'd be starting with the first term being I equal m. So am could just be a number. And then we'll increment by 1, and we'll have I equal to m plus 1. And increment for the third term, I equals m plus 2. The fourth term, now we will have added 3 onto m and so forth, and we'll eventually get to our second to last term will be 1 less than n. So in this case, I is n minus 1. And our last term will stop when we reach an. This is the definition of summation notation, or sigma notation. Now, you could write this as a function instead. Similarly, we could think about each term being a function of the index I. So to make things as complicated as we want, this function can be anything. This function f of I would just be some sort of expression involving I. And every time we want to write the next term in our sigma notation and our summation, we call it a series. If we want to write the next term in our series, then we just need to increment I and plug it into the function. So as a classic example, if we wanted to add up the first 10 positive integers, then we would just have a very easy formula. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 can be simply just represented as a big sum. For convenience, let's number each of these starting with the index of 1. And I equals 1, the first term equals 1. When I is equal to 2, the second term is equal to 3. When the index is 3 for the third term, then that term is just 3. So it's pretty easy to come up with a formula. If we let the starting index equal 1, then we should end at a final index of 10. And we can calculate each of these terms from the index because it's simply the index itself. When you plug I equals 1 into the first term, we get 1. When I equals 2 for the second term, we get 2. Pretty straightforward. Now, a few more examples, and you can see that you can make this as complicated as you want. Now here's the sum of the first 5 perfect squares. Now for convenience, I'll number and label each of these with an index starting at 1, 2, 3, 4, and 5. Now, you can see that the starting index, I equals 1 again, and the final index is equal to 5. Now, if I just wish to make a formula, some sort of function of I, that will allow me to calculate the numbers in this order, 1, 4, 9, 16, 25, it's straightforward. It's really just the index being squared. So this would be represented as I squared. Okay, try a couple more here. What if I wanted to add up the perfect squares 4, 9, 16, and 25? Well, I could be really clever here and just start the index at 2 would be one option. If I start the index at 2, 2, 3, 4, 5, then in terms of sigma notation, I will just start with I equal to 2, end at 5, and once again, this would be I squared. But what if I really love to have all my indices start at 1? Should be doable, but the formula will just get a little bit more complicated. So that means my function that takes I and gives me the value of each term needs to be a little more thought out. Now you see that the index only goes from 1 to 4, because there are 4 terms. It's not simply just I squared, because that would give me 1 plus 4 plus 9 plus 16. What I need to do, in order to get the numbers 4, 9, 16, and 25, is I need to take I have to add 1 to it before I square it. So, there are actually multiple representations for the same series or same sum, if you like. But just in general, you can think about this as being some sort of function in terms of the index with a starting index and a final index, and you just calculate each term as you go and add them all together. Now, as with any kind of new concept, and especially new definition or notation, there's a lot of properties that you may not see intuitively, but a lot of these properties are pretty easy to explain because they are properties of algebra. This big sigma notation is just us taking a bunch of addition, sweeping it all together, and tidying it up. So really, if you think about the properties of addition, things like constant multiples or how we can say addition is commutative, we can add things in different orders, all of that stuff applies here, and it'll give us some properties about sigma notation. So for properties of sigma notation, or if you want to use a term that involves really any summation of multiple terms like this, we call them series. Well, first one is simply just when we have a bunch of terms added together with a constant factor, we tend to factor that out. Well, we apply the same thing with sigma notation. With sigma notation, if we're adding up, let's say, a constant c times ai, so you see here that c is just a number and it has no change as the index increasing, then that would just be a common factor of every term, and we could factor that out. So really, when we take the c, factor that out, we would simply have the sum of all of the terms involving I. We could write that out and expand that to make sense of it. We'd start off with c times a sub m plus c times a sub m plus 1, and keep adding until we get to our last term, which would be c times an. But you see all these c's just get factored out, and we end up with a c in front of our series of terms from am to an. Now, our second property comes from some basic properties of addition, being associative and commutative. Really what I mean by those is when I add 1 plus 2 plus 3 plus 4, I know that if I were to just switch the 1 and the 2 around, 2 plus 1, I get the same thing as 1 plus 2, and that's commutativeness. But also I can completely just change the order of any of those terms. 1 plus 2 plus 3 plus 4 is also the same thing as I want to do 1 plus 3 and then add 2 and 4. Same idea. So using that same idea, here I've got a summation of a series of terms, ai plus bi. So it'd be just am plus bm, am plus 1 plus bm plus 1, and so on. Well, if I just reorder those terms a little bit, I can add all the a's together and then add all the b's together and sum the two results. And it's very similar. I can do the same thing when I have a difference of a's and b's. Simply add up all the a's and then add up all the b's and then find the difference. So those are some very useful properties of sigma notation. Now, last but not least, and this is going to be very imperative for finding areas under some functions in a moment here in another video. If we want to try to find the area using rectangles under a curve, what we can always do is maybe just treat that as an arbitrary number of rectangles and see what happens as that number increases. And this is where we're going to need some of our very common formulas here, especially when we're dealing with polynomials and powers. There are some pretty common sums that we want to take a look at. For instance, adding up the numbers 1 through 10, all of the integers from 1 to 10, you'd figure that people probably have to do that fairly frequently, or at least they had to before, calculators and stuff did most of that for us. Well, there are some shortcuts that we can take because people have developed convenient formulas for adding up the powers of I. Now, just a note here, all of these series are going to be using a starting index of I equals 1. Now, you can always try to apply this to series that don't start with I equals 1 by doing a little clever trickery. You can always try to adjust this index so it does start at 1 and then make some adjustments to the function that gives you each term. But conveniently, a lot of things we're going to be looking at may start with I equals 1 anyways. And so right away, when we have the sum of a constant c, where we're looking at I equal 1 up to n, this is just going to be c plus c plus c plus c. And we already have a shortcut for that. If you have to add up a number 10 times, the same number, well, we just multiply that number by 10. In this case, we take that number c as a constant and multiply that by n. Now, what about that sum of the first n integers? The formula would just be I, and we'd start at I equals 1, so 1 plus 2 plus 3 plus 4, as far as we'd like to go. We can add up the first 10 integers, or if we want to maybe stretch our brain a little bit, we have to add up the first 100 integers. Sorry, the first 100 positive integers. You can see how that would be quite tedious without a nice shortcut. Well, as it turns out, that value is always equal to n times n plus 1 over 2. Now, it's said that a very famous mathematician, Gauss, came up with this as a young schoolboy and quickly impressed everybody being able to calculate the sum of the first 100 positive integers to get 5,050. Now, you can continue this, and it gets a little bit trickier to figure out where these formulas would come from. Let's take a look at the sum of the first n perfect squares. The sum of the first n perfect squares is n times n plus 1 times 2n plus 1 all over 6. And then let's just go one higher power here. Let's take a look at the first n perfect cubes and see what the sum of those would be. Well, if you were predicting a nice clever pattern here, you might be a little disappointed. The sum of the first n perfect cubes is n squared times n plus 1 squared all over 4. Now, there are generalizations of this for higher powers of I, but we could probably leave it there because that safely gets us into the realm of cubic functions at this point in time. Now, I'll keep this brief because we'll be using this in future videos and especially referring back to these four formulas right here. But I'll leave it on one other note here, and that is that this index that I'm currently using is I can be anything. It's really just a placeholder. You could use I for index. You could use K for the index if you wanted really all of your terms to be represented in terms of K. That'd be fine too. You could also use N as the index. However, at that point in time, you wouldn't be able to use n as the starting value or ending value of the index. You just have to make sure that you're using the index as some sort of variable that you haven't already chosen to mean something else. So that gives you sort of a general purpose of what sigma notation is for. You can see how it's pretty tedious to try to write out the sum of the first 100 integers. So we just make a notation so that you don't have to write it out. And then turns out somebody does a bunch of work for you, they find a shortcut to get the first 100 integers. And then you just sum that up by plugging n equals 100 into that third formula there. That's what we're going to be using it for the most part, in integral calculus. Well, we'll see that pretty shortly here. Thanks for watching, and I'll see you in the next video.